So welcome to today's webinar. So today we're going to have three speakers. So Matteo Ruggiero is Professor of Statistics at the University of Torino, and he's worked a lot in Bayesian non-parametrics, but particularly in models connected to population genetics, such as the Wright-Fisher and Fleming-Voigt diffusions, as well as random measures. Filippo Ascolani is a PhD student at Bocconi who is working on non-parametrics, and Guillaume is a senior researcher at INRAE, based at the University Paris-Saclay. He got his PhD from University Claude Bernard in Lyon and did a postdoc in Torino, and has worked on a range of non-parametric problems. So I'll hand it over to the speakers to take us through their talk.
All right, can you see it properly? Can you see my screen?
Yeah, perfect.
Yes. Very good. Thank you very much, Jim. I would like to thank Jim again and Maria for the nice invitation. As Jim said, today I'm going to share this presentation with Filippo and Guillaume. Filippo is about to conclude his PhD at Bocconi. Guillaume is now a position in Paris. And before diving into it, I would like to also acknowledge some other collaborators that were involved in the results, in finding the results upon which this presentation is based. They are listed here. Some are very well known among the younger collaborators. Let me mention Andrea Pandolfi, who's doing a PhD at Bocconi, and Marco Piretto, who's a former MSc student in Torino. So I guess the main message we will try to convey today is that there is a notion called duality, or at least a certain type of such notion which applies to certain Markov processes, which can be useful for Bayesian inference, at least under a certain type of framework that we're going to assume, and about which I will say in a minute. So I will deal with the first part of the talk. I will try to explain how duality can be useful for temporal extension of some classical Bayesian models that are known to, I guess, all the audience today. Then Filippo will take over and tell us how some of these results can be extended to a non-parametric setting and the implications in terms of forecasting observations, some connections with time-dependent polynomial schemes and Chinese restaurants. And then Guillaume will take over for the third part and explain a little bit how these results can be implemented, some approximation strategies that can be used also in order to relax some of the assumptions I'll be mentioning. And then if time allows, I will rejoin for some concluding remarks. So the extension of a Bayesian problem we're going to consider is very well known, and it goes under the name of a hidden Markov model. So really here we can think of our parameter of interest no longer as a static quantity, but as a temporally evolving quantity. So our parameter is going to be described by a Markov chain denoted by X, and this Markov chain is unobserved. So it's a hidden signal or a latent signal. In filtering theory, this is usually what it's called. But we understand this Markov chain as the discrete time sampling of a continuous time process xt, which therefore has a transition function, capital P, characterized by a vector of parameters phi. And these parameters we can see in the statistical model take the role of hyperparameters. So there are several things we need to do here, but first, what's the assumption on the observations? So as I said, this is unobserved. What we observe are data that are collected at discrete times. And the assumption here is that the value of the signal at time k completely determines the distribution of the observation at the same time. So that would be the likelihood of the observations as parameterized by the current value of the signal. And the typical assumption that makes this a hidden Markov model is that given this quantity, this other quantity is going to be independent of everything else. Okay. So this is a widely used model. And in general, there are several goals we may be interested in. The first and foremost would be understanding and describing the conditional distribution of x at time k. So again, this is our parameter of interest that evolves in time. So x at time k given what we call the past observations. So observations up to time k minus 1. And therefore, we would be predicting the signal to one step ahead or several steps ahead. If we add the upcoming observation at the same time k, then we're conditioning on past and present data. And this would be a simple update of the previous quantity, which goes under the name of filtering distribution. Now, obtaining these two quantities essentially requires the same type of effort both analytically and computationally. So we can consider this as part of the same goal if you want, but a different type of effort is required to find and describe fully the so-called smoothing distributions. So here we are now conditioning on the entire data set, but we're still focusing on the parameter at time k. So we are adding, in some sense, future data, and this is typically used to improve previous estimates performed based on past and present data at time k. So this would also be one of our main goals. And once you've done all this, you may be interested in estimating the parameters that characterize the transition law of the signal. So I have previously denoted this by a vector phi, which characterizes the transition of the signal pt phi. And so now we are still conditioning on the data, but we are integrating out the trajectories of the signal conditional on the data. And Guillaume, in the last part of the talk, will also mention at some point how to simulate from the posterior transition of the hidden signal given the data, which is a key component of the strategy for estimating this parameter. Now, some examples. In a very simple scenario, we can take the state space of the parameter to be R plus. So our parameter is this evolving trajectory in R plus. This could be a Cox-inverse velocity diffusion or CIR, which is widely known in mathematical finance, but is also used in population genetics. It can be seen as a continuous state branching process. And the state of the signal determines the shape of the likelihood. So here, for example, the signal as a small value, and this determines that the likelihood is concentrated around the origin, whereas here, at a different time, the signal has a higher value, and therefore the likelihood has probability mass, which is more spread over its support. Okay, so in this case, the assumption would be to have Poisson observation. So marginally, this would be first course in statistics Bayesian model, whereas with the same qualitative interpretation, we can assume the signal to be a right Fisher diffusion on the 0-1 interval. So we will be taking this to be the 0-1 interval. This would be a degenerate diffusion. And we can think of this as an evolving Bernoulli parameter, if you want, or the percentage of a species in a two-type population that changes in time because the population evolves. So the qualitative interpretation is the same. The likelihood would be Bernoulli or binomial, as we would expect in a typical Bayesian model. We can also step up to k dimensions. This would mean the k minus 1 dimensional simplex. So the temporally evolving parameter is now a vector. And this in particular, in this case, would evolve in this simplex. So it would be a point evolving as a diffusion in this simplex. And given the current value of this point, this determines the shape of the likelihood. In particular, it gives the probability of selecting a certain category in a categorical or multinomial likelihood, which changes in time along with the parameter. We can make a further step and go non-parametric. So the state space, as Filippo will argue, can also be taken to be the set of probability measures on a complete and separable metric space. In this case, the temporary evolving parameter would be a Fleming-Biot diffusion. And this model is closely related to Dirichlet processes, so to the cornerstone of Bayesian non-parametrics. Now, what's the relationship? Here, I'm plotting an hypothetical realization of the process at time t. So that would be the equivalent of realization of a Dirichlet process, but now it's the state of the process at time t. And this process evolves. So maybe at time t plus s, this atomic measure not only has frequencies that have changed, but also the support may have changed. So you can appreciate that in this part of the support, there was a negligible mass, and now the mass has increased. All right. And a qualitatively similar argument can be done for the so-called Dawson-Watanabe diffusions, which can be seen as time-evolving gamma random measures. So this now would be a gamma random measure, and for each t, the realization of this random measure will give the intensity measure for a Poisson point process. So we will have results for all these processes in various shapes and forms. And what is the role of duality in all this, even before stating what duality is, which I haven't said yet. So there is obviously a vast literature on filtering. And in particular, I would like to mention here the notion of finite-dimensional filtering, which is obtained whenever the filtering distributions, so here we are evaluating the signal at time k, conditional on past and present data, whenever the filtering distributions are in the same family of kernels as the stationary of the hidden parameter, the hidden signal. So the classical reference is the Kalman filter, which involves Gaussianity assumptions. And in this case, this would entail a linear cost of the inference in the number of observations. That means that in order to characterize these distributions, it is enough to update the parameters, as indeed happens with the Kalman filter. And in all these finite dimensional filters, either Gaussianity or the finiteness of the state space are typically involved in various combinations. The problem now is that very often, even in one-dimensional models, the transition function of the signal is intractable. And this would determine that all filtering distributions would be infinite mixtures. So one would typically resort to a stochastic approximation of this, but this is not what we're interested in. We're interested in finding some sort of middle ground, if you want, which relates to the notion of computable filtering. So a filter would be computable if the filtering distributions can be described as finite mixtures of elementary kernels which belong to a certain class, typically of the same form as the stationary of the signal. If we're able to do this, then we would be able to do an exact computation for evaluating these filtering distributions. So these are marginal posteriors for this temporary evolving parameter. And this would entail a polynomial cost in the number of observations. So it's not ideal, but it's not dramatic. It's a sort of middle ground between a finite dimensional filter and resorting to a stochastic approximation. So what's the role of duality in all this? Duality is what is going to make, under certain condition, this filtering distribution be finite mixed. So up to this point, this is an assumption. Duality is what's going to do the trick, and in certain models, yield exactly this type of condition. So what is duality? We say that a Markov process X has dual process M with respect to a function. So small digression, there are various types of dualities. Here we're interested in the so-called duality with respect to a function. This function essentially has these two arguments, and these processes are dual if this identity holds. So here we have on the left-hand side the expectation of this duality function with respect to the law of the transition law of the forward process X, so our parameter of interest. Whereas here the expectation is taken with respect to the transition law of the dual process. This could seem a little bit cryptic. I will give a couple of examples in a minute, but it's interesting to note that the notion of duality goes back to some works of Levy and Lindley back in the 50s. There is a nice recent survey by Johnson and Kurt, and duality is also treated extensively in the book by Ether and Kurtz. So among various applications of duality, which also concern the weak uniqueness of the forward process, what's of interest for us is that if the dual process has a simpler space than the forward process, then this is going to help with the computation, because we're going to move, roughly speaking, the computation from an uncountable state space to a discrete state space. So some examples. There are various types of dualities out there. Two types we're interested in are called moment duality, because the duality function takes this form. In the simplest case, the parameter is described by this SDE. This would be really the simplest right-Fisher diffusion on 0, 1. And the dual process, interestingly, is a death process on Z+. This is related with Kingman's coalescent, but the intuition is that this M here is determined by a sample from the underlying population at a certain time. So we can think as X as being the proportions of ones in a population of ones and zeros. We sample from the underlying infinite population. This determines this M. If we track these individuals backwards in time, so up to time minus t, we're going to observe the lineage, the genealogies of these individuals that coalesce progressively until we get to the most recent common ancestor. So there's a vast literature on these mathematical results concerning moment dualities and this big family of diffusions that relate to the right-Fisher class. Another type of duality can be called gamma duality, because this is the type of function that does the trick. It relates to the CIR diffusion, and we can have two different types of duals. One is a death process with a deterministic companion, let's say, and the other one is a birth and death process. So here there's an interesting question that arises already, and Guillaume will tell a little bit about how we can interpret this dichotomy, this existence of two different duals, and what it can mean in terms of inference. So the result I'm going to state is the following. We are interested in smoothing distributions. So we are evaluating the law of the signal at time k, conditional on data at adjacent times. This is the simplest, but the key result that enables us to derive all the quantities that we need. So we are in k dimensions now. We assume the forward process is reversible. So that's the parameter of interest again. It's reversible to respect to a density which is conjugate to the likelihood. So marginally, we have classical conjugacy. Then, if we're able to find a death process dual, we're going to have that these smoothing distributions are finite mixtures of this type. So the distribution of this guy here, conditional on these observations, even when the transition function is intractable, reduces to a finite mixture. And the interpretation here is that the data obviously carries some information about the signal, and this mixture modulates this information, and some of these components carry less information than that provided by the data. How these components are weighted is where the dual process gets in. So these weights can be described explicitly, and they are determined by the dual process. So the dual process tells us how to modulate the information provided by the data at a different time point. Now, there are a series of consequences I don't need to get into, but this is really the key result that enables us to do everything that's going to be shown next. So in the two examples I mentioned, the CIR, the stationary is a gamma, the observations are Poisson, so marginally everything is easy peasy. We have this gamma type duality, and so given data at adjacent times, the smoothing distribution is going to be a finite mixture of gamma densities which carry less information or the full information given by the data, but these are modulated by the dual in terms of the mixture weights. And about the right feature with mutation, here we need mutation because this gives the stationary model. The stationary is a beta. The observations are binomial. So the observations are going to give you counts of ones and zeros in this population of two types. The smoothing distribution is going to be a finite mixture of beta densities. Now, Filippo, in a minute, is going to tell you how these results can be extended. He's going to go directly to the non-parametric framework, skipping the k-dimensional framework, which is included in my assumptions. But first, I want to give a hint about something Guillaume is going to talk about at the end of this part, because sometimes we're going to observe birth and death duals related to some models. So I've been mentioning death process duals. The state space is discrete. That is what does the trick in terms of a finite mixture. But birth and death process duals arise in the CIR model, in various Wright-Fisher model. This is of particular interest for us. Wright-Fisher with selection has only a birth and death process dual with intractable rates. So we would be interested in understanding what happens if you have this type of dual. And the problem is that now you no longer have finite mixtures, you have countable mixtures. So what you can do, which Guillaume will talk about, is resort to some type of approximations using particles. And when we have several options, we can compare the performance of filtering based on these several options. So at some point, Guillaume will compare exact filtering with filtering based on a death dual, birth and death dual, and as a benchmark, we will keep a bootstrap particle filter to evaluate our performance. So I'm going to leave the floor to Filippo, who's going to talk about the non-parametric extensions.
So thank you very much, Matteo. You should see my screen.
Yep.
So thank you very much again to the organizer for this nice event. As Matteo said, duality is a very useful property because it often allows you to study a stochastic process in a much more amenable way. And the goal of the second part of this presentation is to show how we can exploit and apply duality in a Bayesian non-parametric framework. So since we are non-parametric, we are working with infinite-dimensional objects, so we need an infinite-dimensional signal that in this case is the Fleming-Biot process that Matteo already mentioned. So, you can think of the Fleming-Biot process as a stochastic process over the space of discrete probability measure that has some nice analytical properties. In particular, you have that the marginal of the process at each time t is given by the law of a Dirichlet process. That is probably the most well-known object in Bayesian non-parametric. So here the idea is that this Fleming-Biot can describe the temporal evolution of the distribution of time-dependent observation. So we have that at each time t, we have that observation at time t are distributed according to the realization of the signal at that time. So essentially, we are in a dependent Dirichlet type setting. Moreover, as an alternative that we do not consider here, we could study the Dodon-Watanabe process that, very loosely speaking, can be thought as the unnormalized version of the Fleming-Biot process, as the gamma random measure is the unnormalized version of the Dirichlet process. So in a more statistical sense, we could use the Dodon-Watanabe to study the evolution of Poisson point process observation. Today, we will focus on the Dirichlet case, so we will focus on the Fleming-Biot, but notice that you could have essentially the same result if you look at the Dodon-Watanabe diffusion. Now, as Matteo already pointed out, the Fleming-Biot diffusion has been introduced in a completely different framework in the field of population genetics to study the evolution of a population. So the idea here is to exploit its nice mathematical properties, for instance, the fact that it is invariant, that the Dirichlet process is the invariant distribution in a statistical framework. So the idea is that we would like to compute the posterior distribution of the signal given observation at different times. But here we have a mathematical problem. Essentially, the issue is that the transition function of the Fleming-Viot process is intractable, in the sense that it depends on an infinite measure that we're not able to evaluate. So the question becomes whether we are able to compute the posterior distribution of the signal at time k, conditional to the observation, and whether this distribution is nice enough, both from an analytical and computational perspective. Moreover, since we are statisticians, we are interested in the impact of this diffusion on the observables. So essentially, we would like to compute the predictive distribution of the data conditional to the observed data point. So essentially, in a mathematical perspective, we would like to be able to integrate out this infinite dimensional signal. And it turns out that those two goals can be achieved exactly thanks to the nice duality properties of the Fleming-Viot process. Indeed, it can be shown that the Fleming-Viot is dual with respect to a pure depth process. And in a statistical perspective, as Matteo said, this means that the filtering and prediction distribution can be computed at finite measure. To be more precise, in this paper of 2016, it has been proven that if you consider the distribution of the signal at time k conditional to data at time k minus 1, we have that this distribution is a finite measure where each element is given by a Dirichlet process updated with a subset of the observed observation. So essentially, if n is the multiplicities of the observation at times k minus 1, we identify all the subset of these multiplicities that identify the element of the measure. So here the idea is that we run a depth process from time k minus 1 to time k, and we keep only the survived observation. In a statistical perspective, this means that the depth process measures how the past information becomes obsolete if you want to make inference in present time. And in order to clarify this point, let me consider a very simple illustration. So first of all, we are at time 0 with no observation whatsoever. So we just have the prior distribution that is a Dirichlet process. So this is characterized by the node 0, 0. That means that no data points have been observed. Now assume that at time 0 we collect 3 observations, 2 of which are equal. So it means that our multiplicities are now 2 and 1. Assume that we want to make the prediction step, and so you want to compute the distribution at time 1. You want to compute the distribution of x1. Well, it means that we need to run a depth process from 0 to 1, starting from the node 2, 1, and we need to consider all the possible arrival points of this depth process, and each node, each possible arrival point corresponds to an element of the measure. So this clearly explains why we expect to have finite measure in this setting. Moreover, notice that we call this a partial conjugacy property in the sense that we could add additional data points, we could consider filtering at different times, but still we would be in the class of finite measures. And moreover, the weights of the measure could be explicitly computed recursively. So essentially, we always work in the nice class of finite measures of Dirichlet processes. Now, as I told you before, we are not only interested in the posterior distribution of the signal, but also in the predictive distribution of the observation. So we would like to integrate out this infinite dimensional object. Well, it turns out that if the posterior distribution of the signal is a finite measure of Dirichlet processes, then the predictive distribution of the data is a finite measure of polyhedron schemes. In particular, if you want to sample a new observation at time k, conditional to observation at time k minus 1, this observation will be either a completely new value from the baseline distribution P0, either an old value from the distribution Pi, where Pi is the empirical distribution of the survived data point. So essentially, once again, the depth process tells us which information is still available at time k if we have information from time k minus 1. Moreover, if the if the polyhedron scheme can be described through the well-known Chinese restaurant metaphor, in this setting, we have a generalized Chinese restaurant metaphor that describes the clustering structure that is induced by this temporal diffusion. So we have clustering at different times. And this new metaphor is characterized by a conveyor belt that essentially describes the temporal evolution of the dishes that are available to the different customers at different times. Now, as for the moment, we have assumed only two conditions on past data. However, it becomes natural to wonder what happens if we incorporate both past and future observation. And so here the idea is that if you do that using slightly different proof techniques, you can prove that we still are in the class of finite meter of Dirichlet processes. Moreover, we can identify the element of the mixture in a very natural way. Indeed, we need to identify a subset of the point from the past, from time k-1 that we call I, and a subset of points from the future that we call j. And each element of the mixture is given by the combination of I and j. And then still we are in the setting of finite meters of Dirichlet processes. Moreover, there is the nice additional features that the weight associated to the combination is non-zero if and only if I and j both contain diagrams that are shared between the past and the future. So here the intuition is that the smoothing acts by keeping only those combinations that make the transition from the past to the future coherent in some way. But to clarify this point, let me just consider again a simple illustration. So assume that in the past, at time 0, we have observed 3 observations with multiplicity again 2 and 1. Instead, in the future, at time 2, we have observed 4 observations with multiplicities 2 and 2. Moreover, we have a observation y1 that is shared between the 2 moments. Now, if you want to compute the smoothing distribution at time 1, the result that I have shown to you before means that we need to eliminate all the nodes that do not contain the shared observation y1. So essentially, smoothing means that we eliminate some of the possible combinations, so we eliminate some of the element of the mixture, and so we have a smaller uncertainty. And this is very intuitive because it means that incorporating both past and future information makes the inference more informative. Let me just add that here we have shown the result for the signal, but even in this case, it is possible to compute the predictive distribution. That is, you can sample new observation in the present, conditional to data from the past and the future. So the fact that you're able to integrate out the signal is not only useful because it tells us how to sample new observation, but we can use that to prove some new statistical properties of this model. So, for instance, we are able to show that the support of the Fleming-Biot distribution, the weak support, is full. And so it means that it is a proper non-parametric method in the sense that any distribution that belongs to this set can be approximated with positive probability. Moreover, we can use the knowledge of the predictive and smoothing distribution to compute the correlation between observations at different times. And this yields a nice formula because you have that the numerator essentially depends on that process, and it's a probability that the observation at time t is still alive at time t plus s. So once again, you see very clearly how the dual process tells you how the temporal dependence is induced in the model. So just to wrap up, I have shown you that essentially any posterior distribution of interest, either on the signal and on the observable, can be computed as a finite mixture of simple objects like Dirichlet processes or polyhedron schemes. And so now the question becomes, is it possible to sample efficiently from those distributions so that we can use it for statistical purposes? And for an answer to this question, I will leave the floor to Guillaume.
Thank you, Filippo. So let me share the slides. Very good. So thank you, Filippo, for the very nice preparation. Let me now go back. So I'm going to go back to the finite dimensional case, but I'm going to use the picture that Filippo made, which is that, and I'm going to explain that these duality methods, they allow a lot of nice constructions, but they also allow to construct very efficient inference algorithms in a variety of models. So as you might have guessed already, the main challenge that you have is first so we translated the filtering problem or the inference problem on a dual space which is discrete. And the main computational challenge that you encounter when trying to deal with the inference on this dual space is having to compute all these transitions down. So whenever you have new observations, you start giving a positive weight to some of the states on that discrete space, and it can go as high as you want depending on the number of observations. And then in order to perform the filtering, and in particular to compute the prediction step that is involved in the filtering, you need to compute all transitions down in this graph. So for instance, starting from that node, you need to compute all the transitions to the nodes below, and you need to do this for all nodes. So hence the polynomial complexity that Matteo hinted at when he introduced the method. So let's say still a computable problem, still a finite number of transitions to compute, but the number of transitions grow polynomial. So now for a small amount of data, it's still possible to implement this and to perform the computation. However, as the amount of data grows larger, we would like to design some efficient approximations of the exact solution. And two options naturally come to mind. One is to prune the mixtures, so actually not compute all these transitions, but just select the states with the larger weights and compute the transitions only for these states. And in practice, this means that you will only keep maybe a finite number of states at each observation in time, and so you bring the complexity to something linear in time instead of having a polynomial complexity. Another option is not to compute all the transitions, but to try to sample some of the possible transitions. So you would sample some, you would do a particular approximation where you approximate this let's say all the weights on these states by a finite number of particles, and then these particles you propagate forward in time to approximate all the transitions down. So this is very similar to the type of strategy you use in bootstrap particle filtering. And as Matteo already said, to evaluate the efficiency of our approximate methods, we will compare to the standard approximation for this type of model, which is particle filtering of the original model, so without using the duality relation. And the first, the empirical results of this pruning strategy, so here I'm only speaking about the pruning, are very dramatic. So here in this bottom picture, you can see a graph that shows the absolute error on the likelihood. So let's say the approximation error as a function of the computation time. And this is time relative to computing the exact solution. And you can see that in violet, you'd have the time and error of the particle filter. And here in color, in the other colors, you would have the time spent and the error for the approximation that you obtain by pruning. You have different points because you can increase the computational effort by either using more particles in the particle filtering strategy, or pruning less aggressively, let's say, in the pruning strategy. So the pruning algorithms allow to recover the hidden signal and provides orders of magnitude improvement in terms of performance. So these are results only for the filtering distribution on the CIR model, but the results are pretty similar for the Wright-Fisher model. And also these results also hold for smoothing, because the cost of smoothing is related to the cost of filtering. And the cost of parameter inference in general is also related to the cost of filtering, the high. So just one further mention, Matteo also explained that using duality, we're not only able to perform filtering, but also to compute smoothing and get tractable expressions, tractable solutions to the smoothing problem. And this is interesting because obtaining the smoothing distribution actually allows us not to perform only inference on the parameters conditional on the data, but to tackle the inference in a Bayesian framework and do joint inference on both the parameters and the hidden trajectories. So in order to attain this goal, you need to obtain, or you need to have available the smoothing distributions, and using the pruning strategies, we can efficiently compute them and perform, for instance, here joint inference on the parameters and trajectory of the Cox-Singer-Selros model. So pruning is an efficient approximation strategy. However, the approximation is not very well controlled. It gives good empirical results, but it's natural to consider other type of approximations, and most particularly stochastic approximations. So I'm going back to the example of filtering because most of the fundamental ideas are present already. So as per the result described by Matteo, the filtering distributions are in a finite mixture of distributions. So a natural way to approximate this filtering distribution is just to sample particles with weights according to the weight of the mixture components, and then use another finite mixtures, but with the particle approximation. So it's basically a particle approximation of the mixing measure of your finite mixture here. Then the next step is to take these particles and propagate them forward in time according to the dual process. So you would use the dual process, let the particle evolve, and then you will get a new finite mixture, which approximate the predictive distribution. This is, again, very similar to the type of approach you find in bootstrap particle filtering. Now, what's interesting here is that this type of finite mixtures were really the consequence of having a pure depth dual to our original process. Pure depth dual would mean that you only have transitions downwards in this space. If you start having a approximation or even truncating would work as well, you can start thinking about using birth-test duals instead. So the exact solution is not computable anymore using birth-test dual because you would have an infinity of transitions to compute. And however, if you use a finite approximation, you will only ever compute a finite number of transitions. And let's say this will open the type of the type of models, the number of models that we can deal with, or the number of strategies that we can tackle. So for instance, for the Cox-Ingersoll-Ross model, there is two dual process that we know. One was the pure depth dual that we've discussed at length already. And it has, so the pure depth process is an inhomogeneous depth process. The instantaneous rate is given here, and it has some, so it's not so easy to simulate because of the inhomogeneity. However, there's a closed form expression for arbitrary time transition. So this is a convenient dual. However, you could say, you could look at the birth-death dual, which is this time a homogeneous birth and death process. And so the rates are constant. It's very easy to simulate. You can use a Gillespie algorithm. It might be slow if there's a high rate of events, but it's very easy to implement. And there's even actually a closed form expression for the arbitrary time transition, because it's an example of a linear birth-death process. So using a sampling approximation, we can compare the predictive distribution computed using these two different duals. And basically, as you'd expect, they coincide. It's just because of the duality relation, we can compute the prediction operation with respect to one dual, the other, or we can even switch during the whole sequence, depending on what's more useful for us. So those are very preliminary results where only one set of parameters is considered, and let's take it with a grain of salt. But it's here I'm looking at an error on the whole filtering average over the whole sequence, and I'm looking at the error on the first moment of the filtering distribution, second moment, depending on the various methods. And we see that filtering using the pure depth dual seems a little more efficient with these parameters. But the filtering using the birth-death process also gives good results, which seem to be on par with what you would get with particle filtering. So now, in the case of the Wright-Fisher model, you also have two duals. One is the pure depth dual related to the Kingman coalescence that we've mentioned already, and this is a homogeneous depth process. There's a closed form of expression, but it can be numerically challenging. And also, it's much easier to implement if you have equal observation times, equal time step between observations. Another dual is the birth-death dual, which is a relation of duality with respect to the Moran model, so another model in population genetics. And there is no closed form, but it's another homogeneous birth-death process that's fairly easy to simulate. And it's not harder to simulate with unequal time steps than with equal time steps. And it can also be approximated by a Wright-Fisher diffusion. And it's possible to sample from the Wright-Fisher diffusion using a scheme by Jenkins and Spanner. So the idea that you should have in mind here is that if you don't restrict yourself to pure depth duals, you have a variety of duals that you can play with, and both have different merits or weaknesses that you can exploit according to your needs. So I'm showing the same type of figures as before, where I'm comparing the distributions, the predictive distributions, computed according to the various duals. And this is for a 4-dimensional Wright-Fisher diffusion. So you see basically that they give the same answer, with maybe the bootstrap particle filtering approximation being a little less reliable. Again, this is the error evaluated on the whole filtering sequence, so average of the whole filtering sequence for various moments of the standard deviation. And you can see that the performance can vary. The ease of implementation, of course, varies a lot depending on the dual process that you use. There's no clear answer yet as to whether there's an optimal choice. My intuition is that it will depend on the case, but still it's interesting to know that in your toolbox, you have many more options that you had before. And in particular, this validates the possibility to use a birth-death dual when this is the only dual process that would be available. And this is the case, as mentioned before by Matteo, when you consider the Wright-Fisher model with selection. So I will here let Matteo conclude. Stop sharing.
You want to share? All right, so thank you. I think we're almost out of time, so I'm going to be quick. So we try to show that there are certain types of dualities that in some dynamic Bayesian models yield what we call a partial conjugacy. So there's a closure not with respect to a single type of distributions, but with respect to finite mixtures of these distributions. And in these dynamic models, we have found a middle ground between having the ideal linear cost of a Kalman filter and having to resort to a stochastic approximation because we're dealing with infinite mixture. We can go non-parametric, so we can extend the result to dynamic Dirichlet processes and dynamic gamma random measures. There are nice interpretations in terms of time-dependent polyherns and time-dependent Chinese restaurant processes, which are well established per se in the literature. And in terms of implementation, we can essentially retrieve all the information we need, sometimes more efficiently than using a particle filter, which is sort of the state of the art in this framework. And this idea of the particle approximation, I think this is a key point for concluding, paves the way for using less restrictive dual processes, as is the case in several models of interest. There is some interesting work in process going on, which concerns some of these extended model, concerns Fleming-Veld mixtures that would be mixtures in the sense of law, 1984, but with a Fleming-Veld instead of a Dirichlet process as mixing measure. It concerns inference for an infinite dimensional diffusion of two parameter Poisson-Dirichlet type, which is challenging because the frequencies are ranked and evolve in time, so you don't have information on the types, so you don't have labels essentially. That is pretty much all. These are the main references upon which the presentation was based. So I think I can thank all the audience for the attention, also on behalf of my co-presenters. Thank you very much.
Thank you, Matteo. That was very interesting. So do we have any questions for the speakers? So I had a quick question maybe to get going. So you didn't say too much about the time dependence of these processes. So, I mean, I guess one question is what is the time dependence like? And also, does the duality offer you a way in terms of making models more general? So you talked about in terms of computation, but in terms of modeling, is there some opportunity to use the duality to build variations on these kind of very classical model?
Yeah, so as I was mentioning possibly too quickly in the slide before the references, the next topic.
We are all the colleagues.
Sorry, they're about to close the building. The obvious next step would be from a Bayesian non-parametric point of view, building dynamic mixtures. So modeling distributions on a continuous using kernels, using the dynamic equivalent of a Dirichlet process. So that would be a Fleming-Veld diffusion. So in that case, the static conjugacy that you have with the Dirichlet process is lost, as is lost with a Dirichlet process mixture model. And in the temporal framework, we can still use the duality at the level of the latent variables, which are modeled by the underlying Fleming-Veld process, but in order to account for the observations and so deal with this interaction between the latent variables and the observations, we need to introduce a sequential Monte Carlo step. So that's some work in process. In other directions, we can consider different modeling formulations. So for example, in population genetics, they're very interested in trying to estimate the selection force in an evolving population. But that is challenging because duality is only with respect to a birth and death process with intractable rates. So that's also some work in progress. And that was actually the motivation for compare the performance of using a dead process dual with a birth and dead process dual, because when you have both, you can actually see what's going on and how good or bad you're doing with one or the other. When you have only one, you wouldn't know, but now you have a kind of benchmark to understand what you could do. So that's also some work in progress. I don't know if the others want to add something.
Oh, well, what I would say is that the advantage of this type of population in a statistical setting, so if you consider a dependent Dirichlet processes framework, is that you can exploit all the theory that has been done on those processes to get explicit distribution for the posterior lobes. Instead, if you consider, but in some sense there is a trade-off, in the sense that if you consider a standard dependent Dirichlet process where you put some processes on the atoms and on the weight, you clearly can be more flexible in the specification, but it's in general impossible to derive closed form results for the posterior distribution or for the predictive distribution. So in some sense, it is a starting point where we are able to preserve all the analytical tractability, but still the idea is to go on and try to extend it in a more statistical setting, but still retaining this analytical tractability that make it feasible to perform posterior inference.
Okay, thanks. So are there other questions for the speakers? Okay, well, yeah, I have some questions, but I'm not sure I'm going to bore everyone with all my questions. So I'll just leave it say thanks to the speakers for a very interesting talk. And yeah, we'll be back in May with another webinar. So
thank you very much.
See you later.
Thank you, everybody, for
Thank
joining.
you very
much.
much. Thank you for joining.
Thanks.
Bye, thanks.
Bye.
Ciao.